Welcome. Today's notes worksheet is entitled A Review of the 6 Trigonometric Functions. This lesson just offers us a chance to get a little closure on the 6 functions that we've been investigating over the last several days. So we'll go through some of the characteristics, look at a couple more graphs, and then maybe do an application or two along the way. So why don't we go ahead and start out with the table that you see at the top and get all that information in for our 6 basic functions. Domain, range, period, zeros, and vertical asymptotes. I think the best thing to do would be for me to graph the function just on the screen here and for you to copy in what you think the characteristics are. And then I'll go ahead and do it as well. So hang on one sec. Let's get this going here. There we go. So there's our sine function. Why don't we start with that and see if you can run across the characteristics that you see on your paper. Okay, well here's what I have. So domain, of course, horizontal. We talked about this before. Domain of the sine function, certainly all real numbers. I can take the sine ratio of any number in existence. Perfect. Now the outputs, the sine ratios per se, are in between -1 and 1. And we saw that on the graph, of course. And those values repeat every 2 pi units for the basic sine function. The zeros, it looks like I got a 0 at 0, and pi, and 2 pi, and 3 pi, etc. So 0 plus k pi, or really just k pi would do the trick there. And are there any vertical asymptotes for the sine function if the domain is all real numbers? No, of course not. So that would be that one right there. Hopefully you kind of went 5 for 5 on your paper, and it's looking pretty good. But that's definitely what I got. All right, cool. Let's just go ahead and bring up the cosine function. Same deal. Be great if you paused for a second and try to fill in your 5 before I do mine. But that's what it looks like right there, and we can pretty much use that idea to fill this in. Cosine function, domain, definitely all real numbers. Can take the cosine ratio of any number. But when I get those ratios, they have to be in between 0 and 1. Never have a cosine or sine ratio above 1 or below -1. Awesome, and those values repeat every 2 pi units, as we've seen time and time again. In this case, if you saw the zeros there, I saw one at pi over 2. I saw one at 3 pi over 2, and then 5 pi over 2, etc., etc. So we would say pi over 2, and every pi before and after it. Looks really nice. Any vertical asymptotes for cosine? No, absolutely not. All right, so those first 2 looking good. We did most of our work with sine and cosine. And then we kind of referred to the other 4 there sort of secondarily, but that's all right. Let's see what the graph of tangent looks like, of course. And let's see, I've got tangent of x. I'll hit graph on that. We have some asymptotes in there. Looks good. All right, let's see what we can fill in. So domain, definitely for tangent, is not all real numbers. I kind of wrote it like this. All real numbers except, and then where is tangent undefined? If you kind of think back to all of the ways that we've represented these functions, tangent is undefined at pi over 2 and 3 pi over 2 and 5 pi over 2, etc., etc. So something along those lines right there. Those tangent values do run from -infinity to infinity. So range is all real numbers. That looks nice. Now the tangent values, as we have seen time and time again, don't repeat every 2 pi, but they repeat every pi. So shorter period for tangent compared to sine and cosine. Zeros, again, if you take a look at that function, if you still have it on the graphing calculator, excuse me, I think you're probably seeing a 0 at 0 and pi and 2 pi. So that's, I believe, what we got as our conclusion. And then obviously we do see vertical asymptotes wherever we have exclusions from the domain. So certainly you're going to see a vertical asymptote at pi over 2 because it's undefined there, and then every pi before and after it. All right, hopefully guys you are 3 for 3, and this is really just nothing more than just some developing the conclusions and a redundancy of what we've seen before. All right, let's go ahead and do cotangent. Bring up my calculator. And I'll do 1 divided by tangent of x. Looks great. So that one is the decreasing graph on the interval. And a little shift on that compared to the tangent. Let's see what we have going on. Definitely I've got vertical asymptotes there. So all real numbers except, and cotangent is undefined at 0, and pi, and 2 pi, etc., etc. That looks great right there. Vertically, though, as we saw, from negative infinity to infinity, so all reals. And tangent and cotangent have the same period. That looks great. Zeros, I think we saw them sort of the opposite of the tangent function, so good way to kind of remember that. And last but not least, vertical asymptotes, of course, where we see the exclusions in the domain, so at k pi. All right, so that pair, tangent and cotangent, work nicely together. Graphs are similar in nature, but some noticeable differences there. And let's get the last two pieces going, guys. Cosecant. Again, cosecant is the reciprocal of sine, so keep that in mind. Reciprocal of sine, we already talked about this before, so I won't go ahead and put the sine function up there. Let's just go get cosecant on this and put it in. All right, looks good. Be great if you could come up with these last couple as well, but I'll leave it to your discretion. So I'm definitely seeing all real numbers, except I've got some values. Remember, wherever sine was 0, cosecant will be undefined, and I believe that happened at 0 and pi and 2 pi, etc., etc. Okay, sort of the reciprocals here, so these were in between -1 and 1. These are on the outskirts of -1 and 1. So something like this. Try not to write that in a more compact way. That's as good as it gets, unfortunately. Okay, period 2 pi. Any zeros here for cosecant function? Nope. Never going to hit that x-intercept unless we do some transformations on it. And last but not least, though, those vertical asymptotes. Got that. Okay, very nicely. Last one. Let's take care of it. Graphing calculator up. Here we go. And 1 divided by, let's go cosine of x. Looks great. Okay, should really look familiar here. You should be able to identify these pretty well, and you'll have to do that as we go through this notes worksheet. So I'm seeing, of course, all real numbers except pi over 2 and k pi. So wherever cosine was 0, secant is undefined. Okay, same deal as before. We've got that piece right there. Period is 2 pi. Absolutely no x-intercepts on secant. And last but not least, vertical asymptotes. And that's looking pretty good. So in terms of these basic 6 functions here, you should be pretty comfortable now with all of these characteristics. Looks really nice. All right, I think I'm ready to kind of move on to the next piece, and let's maybe do an example with it. Now what happens when we develop a more comprehensive function? Could we come up with one of those characteristics? And so we'll go ahead and do this together. Ideally, though, we'll type it in, you pause and come up with it, and then see if it works with what I get. All right, so let's try it. 5 parts, no big deal here. Let's graph them and see if we can come up with the appropriate characteristic. Here we go. So first one is sine. I have x plus pi divided by 2. Again, it'd be great if you typed it in as well. Close it, and then -3. Hopefully our z-trig window will suffice for all these. That one's close, but it's good enough. All right, range it is. That's the only characteristic I'm looking for here. We want the range of this function. So stare at it for a moment. Think vertical on this sinusoidal wave. It's looking like it's fluctuating between 2 values, kind of a max and a min. It looks like the max right up here at -2, min down here at -4, and again, it's fluctuating in between -2 and -4 really the entire time, from max and min. So I'm seeing it like this. -4, it looks to be on the lower end, so I'm going to go with that. But it is fluctuating between these 2 values, inclusive. so definitely include the or equals there. But that's how I would definitely write the range. Again, if you could think about it verbally, then hopefully the translation into the mathematics isn't too bad. But I hope you did see that it fluctuates between -4 and -2 vertically, and so that would be our range. Okay, one down. Let's go get the next. I bring the calculator up, of course, and let's see what we have going here. So cotangent, so 1 divided by, and then tangent of, let's see, x plus pi. Let's get that in there. Looks good. I'll hit graph on that. Not too bad, and all I'm looking for is the period there. A couple different ways you can do this, of course. Let's see if you can focus on this piece. Sometimes it's tough to go asymptote to asymptote here, so going from the y-intercept is not necessarily the best way to go here. I don't know. It's just what you see. I see from here to here is a great repeat. Definitely the graph for sure is in the exact same spot, going in the exact same direction here as it is here. And that looks to be 1, 2 tick marks on this z trig coordinate plane, which of course we should know is pi units. So I'm seeing this as pi, and that looks great. And just one thing to note, of course, do you see the b value in this particular function is just going to be 1? And remember, for sine, cosine, secant, and cosecant, it would be 2 pi over b, but for tangent and cotangent, it's pi over b. So in this case, pi over 1 is just pi. Cool. All right, let's see if we can get the domain on this one right here. It got just, looks like nothing more than a vertical stretch on this, but that's all right. So I have 1.5 divided by cosine of x. That's what this one would look like. So type that in when you get a chance. There we go. And domain. So I do see, and I hope you do as well, those vertical asymptotes pop up. So that's where our graph is excluded. And so there's one at pi over 2. There's one at 3 pi over 2, negative pi over 2, negative 3 pi over 2. So hopefully you're seeing that it is all real numbers, except, again, I'm seeing it at pi over 2 and every pi before and after it. Okay, very good. So we're working through these functions nicely, just kind of picking a particular characteristic and making the function a little more comprehensive than we saw on the table. Nothing should really scare you at this point with these problems, though. Let's see if we can challenge you on the next example or two, though. All right, let's get this one taken care of. So 3 pi divided by 2, looking nice. Zeros it is. So it looks like I just have a phase shift of 3 pi over 2 from the cosine function. What would that mean in terms of the zeros? Well, let's track them. We've got one right here at 0. Looks like another one at pi, 2 pi, negative 2 pi, 3 pi, 4 pi, I'm sure. So again, really not too bad. 0 and all the pi's before and after. Awesome. All right, one more where we get to analyze the graph and come up with one of the characteristics. So that would be tangent of 1/2 x. Throw that in. Looks pretty good. Okay, now it gets slightly harder. This is a great one here. If you could pause this and see if you can come up with one, that'd be great. So I only have 2 up here. I've got one at negative pi, and I've got one at pi. Theoretically, I guess the next one would be at 3 pi. Then the one after that would be at 5 pi. All right. Well, let's see how we're going to translate this. Let's pick our primary one, and I hope you would agree that it looks like there is a vertical asymptote at pi. So let's write that right there. So x equals pi, there is a vertical asymptote there, plus, now how many units does it take for us to get the next one? How often do we see the next vertical asymptote here? Well, if you kind of look at the distance between these two asymptotes right here, it looks like it's 1, 2, 3, 4 tick marks horizontally, which is actually 2 pi units. So it looks like every 2 pi, I should be getting a vertical asymptote here. What do you think? Yeah, I like it. So I have my primary one that I saw at pi, and then every 2 pi after it, so if you want to do a 2k pi or a 2 pi k, it doesn't matter obviously, it's all just multiplication, that would be it. Okay, so a little harder on that last one. Good, nice challenge. All right, so at this stage, I should be able to really give you any function. You can come up with one of those good characteristics. Now, let's see if we can review a few of the problems we've been working on with. Here's the graph. Let's see if you can write the model for it. So it kind of builds up in difficulty here. So I've got letter A, and this one does not require a phase shift. It is definitely sinusoidal. So let's see what we want to do here. And I guess what I would ask you is, do you see the y-intercept is down at the minimum? So what does that mean in terms of sine versus cosine? So again, it looks like the y-intercept is the minimum of our sinusoidal wave. So as a result, sine or cosine? Well, I think we referred to this as kind of the flipped cosine. And obviously, we'll figure that out momentarily. So flipped cosine, and let's see what we want to do. I've got a midline, of course. I always start there personally, kind of get that midline going. So if you want to write this out, you're more than welcome to. If you don't need to, that's fine as well. But I have a midline of y equals 2. It seems to be the case. Amplitude looks to be 2 units as well. That looks really good. And let's see, period on this one. This one's a little harder to kind of figure out, but it looks like it takes me 1, 2, 3, 4 tick marks to go from the minimum to the maximum. So half the cycle is 2 pi units. Everyone agree on that? Half the cycle is 2 pi. So the full cycle there, I think, would be another 2 pi units, which would be 4 pi. So see if you agree on that piece. If I can, I like going from the y-intercept. In this case, you can probably tell from max to max. That's a good way to look at it. And then from here to here horizontally is exactly 4 pi units. Okay. No phase shift required as we figured out this is just a flipped cosine. It would be awesome if you could pause that video and if you could write in what you think the function is, and we'll see how you did. All right, well, here's what I wrote. -2 for the flipped cosine. So -2 cosine, it looks like 1/2 x. So remember, this case was 2 pi over the period. 2 pi over 4 pi is 1/2. So 1/2 x. Close it off. C is going to be 0. Midline is y equals 2, so +2 on the back. Okay, it looks really nice. With these problems in particular, I like to bring the graphing calculator up and just check, see how we did. So I'm going to do -2 cosine 1/2 x, add the 2, and looks really nice, doesn't it? Okay, 1 for 1. Let's see if we can now do something that's a little harder, kind of a review from the day 2 sinusoidal functions worksheet. That's pi over 6 in there, didn't come out great. Notice in this case, is the y-intercept at the minimum or the midline or the max? No. So this one's going to require a phase shift. So this one, if you want to put in sinusoidal function with a phase shift, maybe that would be a good idea. But here's what I'm going to do to get this started. Basically, let me do one thing first. So this is what we're going to try to do for this one. I think I'll do it up here. So this is our sinusoidal function, bx minus c plus d. So a good little review on this piece. In this case, we are going to require a C value to account for the phase shift here. And so let's see what we've got going on. I don't want to jump the gun on us here. First of all, I would do midline. And I'm seeing the midline. Everybody draw it in as well, please, if you would. Right there at that -1. Okay, so D is going to be -1. Great. Amplitude, guys. Let's figure out that amplitude. How far is it from that midline to the max or midline to the min? 1, 2, and 3. So it looks like A is going to be 3, and we could just keep it positive here. Awesome. Let's see what we want to do in terms of a period. So I'm going to start from the y-intercept, and there we go. This should work out nicely. It looks like it's just from here to here, which would be 2 tick marks on this horizontally, which should be pi. So period, everybody, take a look one more time as we write in our b value. Period is pi. So the b value is 2 pi over the period, 2 pi over pi, and 2 pi over pi is going to be 2. Awesome. What's missing, guys? C. What do we have? We have x and y. And that's what we're going to use here, obviously, to find C. So let's put this in as pi over 6 and -1. And then we solve, everybody. Okay, good practice on this. Let's get it going. We have all the info to get C. -1 goes in for y. No doubt about that. 3 is going to be our A value. Again, you can use sine or cosine. It really doesn't matter. I just default on the sine. So 2 times x, or 2 times pi over 6, minus the c, and then plus, -1. All right, very good. Again, just good algebra solving for this. If we need a little trig along the way, we certainly will do it. Guys, everybody bring that 1 on over to the other side. And when I do, I get 0 equals. This looks great. And if you don't mind, I like cleaning this up a little bit. 2 times pi over 6 would be 2 pi over 6. And 2 pi over 6, of course, is pi over 3. Okay, very nice. Divide by 3. 0 divided by 3 is still 0. Great. And this is going to work really well. I can see it already. So it's kind of like several steps to find that C value. This went away. This went away. Now, guys, it's time to get rid of the sign. And so what we're going to do is the inverse sine of 0. So grab that calculator here and watch how nicely numerically this does work. Inverse sine of 0. And actually happens to be 0. That's perfect. So when I inverse sine on both sides, this goes away, and the inverse sine of 0 is still 0. How great. And then we do want to go ahead and solve for C here. I'm hoping that you would see, and again, you could do this a couple different ways. I like bringing the C over here, and then whatever's over here I bring over, but I hope you agree with me that it looks like C is pi over 3. Perfect. I think we're ready. So we had all of these pieces that worked out really well. Let's go ahead and write our function at this stage. So I have now y equals. A was 3, so I've got 3 sine. It looks like 2x minus the pi over 3, so minus c. So this would be considered a positive phase shift, so minus pi over 3 and minus 1. See if that works with the numbers that I have on the screen there. I'm going to box it up. And obviously, I do want to grab the graphing calculator just to verify that everything is legitimate. So let's go ahead and do that, and then we'll move on to the next. Okay, so here we go, everyone. Let's take a peek. 3 sine 2x minus pi divided by 3. Close it off. How about a minus 1 on the back? And let's just see how well it matches up there. What do you think? Yeah, pretty much spot on, isn't it? Good stuff. All right. So let's go get these last two. All right, so this one looks to be, letter C, looks to be either the cosecant or secant. And I guess I would ask you, which is it? Think about, the way it played out. Think about sine and cosine, and as a result, cosecant and secant. Which is the one that has the y-intercept as a function value as opposed to the y-intercept as an asymptote? And if you remember, I'm going to go ahead and just bring it up. If you remember, basic function-wise, I think we want secant. So take a look. Do you see the secant is the one that has that y-intercept right there, kind of like this? So everyone see that piece, how it matches up? So I think to avoid any type of phase shift, I think secant is the way to go. Does it look like this has been kind of moved up, vertically shifted? Instead of the midline being at 0, it looks like the midline is now at 2. So are you okay with me saying it looks like a d value of 2? And by the way, secant function, if you want to write that down. And then the only other thing that we're going to work with, because we can't really tell in terms of amplitude, so don't worry about A. We're going to keep it as it is. But really what I'm wondering about is really the B value. So everyone take a look at that if you would, and can you tell me the period here? What would be the period of this particular function? And as a result, what would be the B value of our secant function? So how about from there to there, guys? What's that period? So the period seems to be pi over 2. So the B value is 2 pi over that. And we've seen this once or twice before. You can kind of clean this up nicely here, but long story short, should probably get 4 as the B value. Okay. Well, I think that's really all we need here. Again, we chose secant because it matches up nicely. D value is 2. B value is 4. No phase shift. And we're not going to really worry about A. That would be a little too tough to kind of tell here from these graphs. But I think we're ready to roll. So how about secant of 4x? Close that on off. And add the 2. Okay, I think it's a winner. All right, very cool. Let's bring it up and see if we can type this one in. This might be a little hard to type in, but I'm going to go ahead and give it a try here, and then if I have to modify it a little bit, I will. So there we go. That's pretty much what we have going on there. I'm going to hit graph, and not perfect, but does it look like it matches up with what I have up there? Yeah, it's good. Okay, 3 good graphs down. Let's take care of this last one, and then we'll do a little calculator work to wrap this lesson on up. So letter D. What are you thinking here? Tangent or cotangent for this one? See, to me, it looks like we probably want cotangent as it is decreasing. That seems to be the case right there. And we're going to have to kind of tweak this a little bit. I don't know if there's a phase shift on this. Let's go ahead and bring up the cotangent function just once and just see if we can get this one to work. So 1 divided by tangent of x. I hit graph, and so that's what we have going on right there. Now the only thing that sort of happened is it looks like from here to here, it looks like things have been horizontally compressed, right? The period is less. And so I think what we're going to end up doing here is just change the period, and so as a result, change the B value. Let's see. So it looks like, in this case, period is pi over 2. So the B value, remember in this case, is pi divided by the period. And so if we do pi divided by that pi over 2, let's be a little careful on this end, I end up getting 2. And again, if you feel free to ask on this if you're not sure how to simplify that piece, just let me know. But if I do pi divided by pi over 2, should get 2 as an answer there. So I think, and just to kind of get this piece moving along a little bit, it looks like we want cotangent because that's what really matched up nicely there. And the period is less, and so what that means is the b value is going to be a little greater, and I think we're going to go cotangent of 2x there. Well, let's see. You know, some of this may be a little trial and error as you look at this and you try to match some graphs with some functions. Again, if one thing doesn't work, see what went wrong and try to make the necessary adjustments. But if you look at what I just graphed up there, it seems to match the graph on the screen pretty nicely. All right, cool. So good review, working over all 6 functions, some good problems with this. Notice you're not point plotting and you're not graphing them yourselves. You know, I just sort of feel that's a little unnecessary. But these are some good problems that allow you to really think about the characteristics and some good higher level thinking as well. All right, guys, last one. Example 3. So I actually called Excel Energy, and they were able to kind of give me this information, and let's go through it. So Mr. Meyer's monthly gas usage in therms over the course of a year is shown in the table, and so just finding a sinusoidal regression for the data. So this is a quantity that peaks and valleys, winter to summer, and also is cyclical year after year after year. So I don't know if it's perfectly sinusoidal, we can kind of see, but let's see if we can come up with a regression nonetheless. All right, so I'm going to have to bring this over here. So guys, if you would, last time through, let's go Stat, go into Calc. If you have anything in there, just clear it out. Remember, just go up and hit Clear and then Enter on it, and should get rid of that. So over the course of the year, so month 1 through 12, type that in, and I'm sure you can type in quite a bit faster than me. Almost there. Perfect. All right, now let's match it up, everybody, if we could. So in this case, therms in the winter seem to be quite a bit more than in the summer. So in January, for our house, the usage was 130. In February, it goes down a little, 113 as the temp goes up, 94, etc., etc. And as you can see, it's going down and down as we get closer to the summer months. Cool. Let's see, almost there, guys. Hopefully you're with me on this piece. And by the time we get back into November and December, it's gone back up again. All right, very cool. So that was over the course of 1 year. And let's go ahead and just take a look at this. I'm going to actually just turn my stat plot on. If you could do the same, that would be great. And let's go ahead and zoom number 9. And so, is it perfectly sinusoidal? Probably not, but sort of an interesting pattern nonetheless. Let's see if we can come up with a regression now. So I'm going to go Stat, move it over to Calc. Here we go, guys, all the way down to Sin Reg. Hit Enter. I like putting it in, so you can just give me a moment on that piece. Put it in the y equals, and there we go. Not too bad. So it looks like I've got to a few decimal here. Well, let's see. It looks like exactly 67. And then sine. Well, you're the lucky one. You have your calculator right in front of you, but I've got about 0.391x. Let's see what that C value was here. And they do a plus with this. That's the only difference. Just be a little careful on that. But plus 1.841. Close that on off. And let's get that D value on the back, and it looks to be about 80.489. And there we go. Looks nice. Obviously, there's really no prediction we're making here because x is in months and y is in terms, and we kind of have that, but sort of interesting to see nonetheless. I'm going to go ahead and just bring the calculator up one last time. And I'm going to hit graph. And you can see, is it perfectly sinusoidal? Nah, but it's really not bad. Still has that good look about it. Okay, so some good problems to really put some of these functions together. Hope we can get some closure on this piece, and then on to the next unit. Thanks for listening, of course.